All right, I'm going to talk through how to do worksheet 12, number 1. I'm going to solve it both ways, which is what you're going to do on the rest of this worksheet. I'm going to start with using equations. So the first thing I'm going to do is read the problem, and before I do that, I'm actually going to underline all the numbers. But we can't just pay attention to the numbers and the units. Even though the units give me a really good clue of what those quantities are, I have to read the context too. And this problem is actually a great example of that. So a water buffalo is running away from a Bengal tiger. We watch the water buffalo increase its speed by 1.2 meters per second every second. So when I read that, this seems like it would just be a velocity. Oops. But with every second there, that tells me it's 1.2 meters per second. So that's the acceleration. For 5 seconds, that sounds like the time. And then it makes it back safely. Its velocity at this time, or at 5 seconds, is 9 meters per second. So that is the final velocity, or what we often just call v. So we've got our acceleration, our time, and then our final velocity. The question we want to answer is how far did it run during those 5 seconds? So how far, that's the displacement. And so we use change in x or x minus x initial. Okay, so I want an equation that has all 4 of those variables in it, a, t, v, and delta x. But unfortunately, I don't have one with just those 4. I have ones with lots of variables. So I'm going to start with the equation that has what I'm looking for in it. And right now we only have 2 physics equations, just those first 2 at the top left of the green equation sheet. And this one has delta x, which is what I'm looking for. So I'm going to start to plug some information in. So my acceleration is 1.2. The time is 5 seconds. Can't forget that time. But I actually don't know my initial velocity. This 9 meters per second is not the initial velocity. It's the final velocity. So in order to solve for the displacement, I need to solve for the initial velocity first. And to do that, I actually need to use my first physics equation. And it's okay if I start to use this delta x one and figure out I need to solve for initial velocity first. That's very normal, and that's a typical part of physics problem solving. So I'm going to use this equation to solve for initial velocity so I can plug it into this equation. So my final velocity is 9. My acceleration is 1.2. And my time is 5. Excuse me. Then I'm going to try to solve this for the initial velocity. So 1.2 times 5 is 6. And so I get an initial velocity of 3 meters per second. Now I can plug this initial velocity into this equation. And I'm just using all the same quantities. And so now when I solve this, and I'm doing this very fast, but you can use your calculator, I get an answer of 30. But this is not complete because I need to add units. So this took 2 equations, and most of these problems are going to take 2 equations. So just start with one, see if you can solve for something, and then go with the other and see if you can get the answer. If you start with one like I did on this problem, where I didn't have all the information, you don't need to erase everything. It just means you probably need to use the other equation first to solve for that extra unknown that you had in that equation, which in our case was initial velocity. All right, now I'm going to do the graphical method. And so I can solve using my VT graph and my one physics equation. So the first thing I'm going to plot on my VT graph is 5 seconds. And I'm going to plot at 5 seconds a velocity of 9. So right about there. Now my initial velocity is not 0, so I cannot plot a point there. Luckily, I already used this equation on the left side of my paper, so I'm just going to write down that I already solved this, and it was 3 meters per second. So my initial velocity, or my y-intercept, is 3. Now I'm going to connect those 2 points with a constant slope, or a line, because I have a constant acceleration of 1.2 meters per second, which is the slope on a VT graph. It's the acceleration. Now remember, my goal in this problem is to solve how far. And how far is the displacement. So on a velocity time graph, that's the area from the graph to the x-axis. Excuse me. So I'm going to chop this up into 2 distinct sections and find the area of both the triangle and the rectangle. I sometimes like to do this off the graph just so it helps me really identify what the base is and what the height is. So of my triangle, I see I have a base of 5, and I have a height of just 6. So if I use my formula for an area of a triangle, I should get 15. Almost forgot the 1/2. And then if I find my last little rectangle right here, I have a base of 5 and a height of 3. And I get 15. So to find the total area, I need to add both of those together to get 30. And then my answer is not quite complete because I should have units. But notice both of these questions, I solved them very differently, but I got both answers of 30 meters, and that's the correct answer for this problem.